Hello students. So the next problem is the principal stresses induced at a point in a machine component made of this material 50C4, which have the yield strength or yield strength in tension is 463 minimum square are as follows. Sigma 1 is 200, sigma 2 is 150, sigma 3 is 0. Calculate the factor of safety by maximum shear stress theory, distortion energy theory. Okay, so the principal stresses are given for any machine component. Okay, so machine component, which is there's a difference between specimen and component. Specimen is something that you test in your UTM. Okay, this looks like this, right? So when you pull it, okay, you'll get the test results. Okay, this is the specimen, and using the same material, if you make anything like nut and bolt, okay, screw, your rivets, everything, okay, so that those are called components. So this is the specimen that is only for testing, not for using, not to be used in some machineries. Okay, so machine component we are talking about. A machine component is subjected to a state of stress. Okay, anywhere we have applied some stresses, and they will lead to principal stresses. So sigma 1, sigma 2, sigma 3, these are principal stresses. They the values are given to you, and you have to calculate the factor of safety by using these two theories. Okay, so how to proceed? So let's look at the concept that you have learned, okay, from your factor, so maximum this theories, okay, theories of failure. So going to your theory of, okay, so here see, so maximum shear stress theory, okay, so says that, right? So this is the all the statements of theories of failure. Okay, now look at this. Okay, so till now we have not introduced your factor of safety. So whenever we have introduced the factor of safety in your maximum shear stress theory, see, look at this. What are the okay, oh, I have not written it actually, but when you introduce a factor of safety, okay, that thing has been missed. Okay, so like these are the relations, okay, from with your failure stresses. So the failure stress is nothing but that yield strength in tension. Okay, so this is, look at this, sigma 1 minus sigma 2 SYT. When you introduce a factor of safety, then this will be divided by factor of safety. Okay, so whole thing will be this I mean failure will take place only when these are equal. So we don't want them to be equal. So this divided by factor of safety will make this thing lesser than this one. Okay, understood that? So this is one equation. Okay, then sigma 2 minus sigma 3 equal to SYT by Fs. This is another equation. Sigma 3 minus sigma 1 equal to SYT by Fs. This is another equation. Okay, so out of these three, the maximum one, okay, maximum one you have to find out always, and then you have to see, if you prevent that maximum amount of your shear stress, okay, then I mean, which is, see, let's say this is 50, this is 100, and this is 150. Okay, so if you say that 150 is still less than I mean, say, then you take SYT value as, let's say, 200. Now see, 150 is less than 200, so this whole thing is we are taking the difference, sigma 3 minus sigma 1, the difference. These are differences. 100 is difference, this is difference. So the whole thing is less than SYT. So this is safe. Automatically the others are safe because they are further less than 200, isn't it? But if you take this SYT as, let's say, 100, okay, so 50, the difference here is lesser than 100. This equation is okay. For this it's fine, it is safe, but for this and this, they are not safe. Okay, so you have to always take the maximum difference between them and keep it below your failure stress. Okay, so that is what we did here in this problem. Okay, okay, so right, so here you see, look at this. So in this problem, find out all the differences. Sigma 1 minus sigma 2, 200, this 50, sigma 2 minus sigma 3, 150 minus 0, and actually this is sigma 3 minus sigma 1. Okay, sigma 3 minus sigma 1 will be minus 200, but again I am telling you, you have to take the absolute values here. So the maximum, I mean maximum differences you have to take. Okay, I mean you have to take the modulus of them. So I mean mod of sigma 1 minus sigma 2, this is minus or plus, that is plus only, positive 50, 750, and this is like that 200. So if you compare all of them, so this is maximum, sigma 1 minus sigma 3 is maximum, this is 200. So this is, you have to prevent that one. Okay, so out of the above, this is maximum. So according to maximum stress test theory, this is actually, if you introduce a factor of safety, you have to take this relation. So sigma 1 minus sigma 3 divided equal to your yield strength in tension divided by factor of safety. If you take this as yield strength in shear as SY, then you have to divide it by 2 here. Okay, so like that. So yeah, that is actually we have obtained from maximum shear stress theory only. Alright, so this is your difference. You put the difference, SYT value you put 460 divided by factor of safety. Simply you get the factor of safety from here. Okay, this is 2.3. Similarly for distortion energy theory, if you go to the theory here, okay, what we had here in the theory is, see, in case of biaxial stresses, okay, SYT by FS is equal to this one, the last relation, root over sigma 1 square minus sigma 2 sigma 3. So this is your von Mises stress. So put all the values here and get factor of safety from this relation. Okay, for distortion energy theory. So this is according to distortion energy theory. Put the values and effect of safety you have obtained. Understand? So this is the problem where application of the theories of failure. I mean just to find out the factor of safety from theories of failure. Okay, suitable factor of safety. This is one example. Okay, let's continue to the next problem. So we'll solve few more problems. So look at this. The next problem is, a C frame subjected to a force of 15 kilonewton is shown in figure. Okay, it is made of grey cast iron FG300 and the factor of safety is 2.5. Determine the dimensions of cross section of the frame. Okay, now this is the C frame, okay, which is shown here. So let's actually quickly look at its how it will look like. Okay, now look at this, the C frame here in 3-dimensional. If you draw it in this manner, so this is how it will look like. It is similar to that offset link that you have seen. Okay, similar to that, almost similar. So this is a problem. It is actually just the orientation has changed. Now you understand this, right? Isn't it? So here, so it is pulled like this. Previously compare with the offset one. Offset one was, see, it was being pulled away. Okay, it was like it is bending in like this. It is bending in this manner. Okay, so here also it is being pulled in this manner. Okay, isn't it? Yeah. So sorry, oh no, similar only. In the numerical, this away 15, sorry, this is being pulled away. So 15 is given in the question, 15 kilonewton, which is actually pulling this whole part away. So this is nothing but similar to the previous problem, almost similar. Okay, so look at this. This area is your failure area here, right? Okay, quickly just look at the concept and look at your figure. So from here you see again the same thing. This area is what given, is given 5t into t. So this is actually 5t from here to here. This is 5 times t, and here it is 2 times t. Okay, 5 times t is this one, 2 times t is this small thing. This is 2 times this is t, and this is 5 times t. Okay, now if it fails, it will break. First of all, one type of failure, this is your tensile failure. So due to tensile failure, it will break here. Okay, at this point. All right. Okay, you agree this? So this is the area. In this case, failure area is 5t into t. Okay, area is this. So if you have to prevent your tensile stress, so sigma t is equal to force applied P divided by 5t into t. Okay, this is the tensile failure, tensile stress. Okay, and bending will take place again. So there will be bending here in this manner. Okay, the whole thing is like this, so it will bend, okay, in this manner. Okay, we are pulling in at these two ends, so it will bend it like this. Okay, bending, and this area here will change. Okay, so this area will change, so this will bend in this manner. Okay, so here again understood this. Okay, so this is the area, initial area here, and the final area anywhere you take, either in this direction or that direction. So now you just think that yes, obviously the centroidal distance will be half of 5t. Okay, this distance, isn't it? Just compare with the beam. So this is the beam. Okay, and beam has bent in this manner. Which direction we take? Okay, this dimension we take, just to find out the centroid. Okay, so for here centroid will be half of this distance. Okay, so if you have to find out mb, mb into y bar by I, mb you will find out. Okay, let's talk about these two, y bar and I. Y bar will be 5t by 2. You agreed? Because this is the dimension, and half of that dimension you have to take. I mean this area here, failure area, this is the area, right? So initially it was like this, now it has bent. Everything actually you have to imagine in your mind. So this is your area. So it is similar to this one. So look at this, this is the beam, and after bending the area has come here, so you have to take half of this dimension. No? Here also you have to take half of this dimension. So this is 5t, so this is 5t, and this is t. Okay, so half 5t by 2 is a y bar. And yes, just try to find out this 1 by 12, whether it will be 5t into t cube or t into 5t cube. Yes, quickly think about it. So look at this. So this is the dimension that has tilted. You can just simply like that, the dimension which is tilted or dimension which is oriented will have the cubic index upon this, and the dimension which is parallel to the area, parallel to the axis about which the rotation has taken place, will not have the cube upon it. So this is t. So this is t is parallel to the axis, so t will be written first, and it will not have any cube index upon it. So 5t will have the cube index, okay, upon it, because 5t is will change the orientation. Okay, 5t will come like this. Okay, you agree? Fine. Alright, so simply we have now to find, we are left with this bending moment. So it is similar force, okay, multiplied by the perpendicular distance to the neutral axis. So that is given directly in your problem, 7.5 times t. This is the neutral axis. Okay, so force into 7.5 t is your bending moment. So now you already know a similar problem you have solved. So nothing but what you have to do is allowable stress or permissible stress, which is maximum, which is combination of your bending stress plus tensile stress. Okay, so this is the allowable stress, which you should always keep below your failure stress. So ICOT is a failure stress, keeping it below, we must employ factor of safety for that. So factor of safety is 2.5, and your material is what? FG300. So this is your material. So from here you get ultimate tensile strength is equal to 300 Newton per millimeter square. Okay, so this is 300 by 2.5, which is equal to 120 Newton per millimeter square. Okay, so this is your maximum, your allowable or permissible stress. Okay, now tensile forces is this one, P by A. Force is 15. Okay, 15 into 10 to the power 3. Okay, both sides is same. So you have to take the failure area, that is 5t into t. I told you, see, 5t into t. Actually your figures will be given in this manner, so you actually have to understand this area. This t is actually inside your page, or coming out of the page. Okay, like this. Okay, this one, this is t, and this is 5t. Okay, so that actually you have to imagine in your mind. So 5t into t is a failure area. Okay, very easy to understand. So 3000 by t square. This is your tensile stress, and bending stress is mb into I bar by I. Okay, which is equal to, now see, I told you this is force multiplied by this distance 7.5 t. So force into 7.5 t is your bending moment. So force is 15 divided by 3 into 7.5 t. Okay, 15 into divided by 3 into 7.5 t. It's your force. So this is force and multiplied by the distance. Okay, so here also you can have a look. Here also force multiplied by perpendicular distance to the your neutral axis. Okay, so this is your mb value. Okay, bending moment multiplied by your half of what, that 5t. I told you half of the dimension. So 5t by 2 is a y bar, or your centroidal distance. So this is your centroidal distance 2.5 t. Okay, 5 by 2 is 2.5 st divided by 1 by 12 t into 5t cube. Okay, we have found it, t into 5t cube. Okay, so once you just understand everything, you can just solve it very easily. So now you will get an equation like this, 37,000 by t square. Okay, which is equal to bending stress. Now simply you have to combine them. So combine them, add them together, this plus this. Okay, so this is the maximum value of your permissible value. So permissible value we are not crossing. That means actually the meaning of this thing is what dimension will give you the I can say permissible value. That means a value of t equal to thickness equal to this much will give you a permissible value of 120, which is much below the breaking value, as SUT value. SUT is 300. No, so when you employ t equal to 15.81, you will get a safe, or actually you will actually obtain a stress of 120 only, which is lesser than 300. So actually we are going like that. So you have to find out what should be the safe applicable stress for us, and actually you are going to find out what dimension will give you that stress. That is what we are doing here in machine design. Okay, so sigma max equal to, this is the combination of bending and tensile stress. We can just directly add them together. So this is 3000 by t square, this is sigma t, and this is sigma b is 27,000 by t square. So from here you solve t and obtain t. Understood? Okay, so this is your problem of similar type that we have solved. Okay, so I'll continue the next problem. Okay, thank you.